Numerical Computation, Chapter 6, Video 3. We now define norms for matrices. As we said earlier, matrix norm is defined in terms of the corresponding vector norm. For a different vector norm, you will get a different matrix norm. So let A be a matrix, a square matrix, and X denote a vector. The matrix norm for A corresponding to the vector norm for X is defined as following. So norm of A equals to the maximum of this expression here, that is A times X, taking the vector norm, divided by the norm of X. And the maximum is taken over all X that's not 0, meaning where the denominator does not equal to 0. Let's look at some properties for the matrix norm A. So first one, since the norm A is the maximum of this expression for all X, then for a certain X, the A norm is bigger than this expression. That's by definition. This means if we multiply both sides by X norm, and I can keep the inequality sign, that means A times X, where A is a matrix and X is a vector, and taking the vector norm of it is less than or equal to the A norm, matrix norm, times the X norm, the vector norm. Now let's see if we have an identity matrix, what will be its norm? Well, if A is an identity matrix, then A times X is just X. Here you will have X norm over X norm. If X is not 0, you're taking max over a constant 1. So therefore, the matrix norm of identity matrix is always 1 in whichever norm you work with. And last, we have this identity also, a matrix A times a matrix B. Then you get a matrix and take the matrix norm of that. That is smaller than the matrix norm of A times the matrix norm of B. Now, we will take a couple of examples of matrix norm corresponding to the vector norms that we have talked about in last video, and these are given without proof. Okay, so the L1 norm for matrix A corresponding to the L1 vector norm is the following. So you take the maximum of the sum of all the 8 elements Aij in absolute value, and if you run first summing up for I from 1 to n, then you are adding up the ith column. So you add up each column, take absolute value first, add up each column, and you get n numbers, and then you take the maximum over all those numbers, and that's the L1 norm. Now the L2 norm corresponding to the L2 vector norm is the following. You take the maximum over lambda I, where the lambda I is an eigenvalue of A. So this norm is more interesting because it gives me a chance to talk about eigenvalues. So the L infinity norm associated with the L infinity norm of the vector is very similar to the L1 norm, except that I switch the order of X and J. So what you do now will be that after taking absolute value of all the entrances in A, and you add up each row, and then you have n numbers, and then you take the maximum among all those. Okay, so let's talk about eigenvalues for A. So if lambda is an eigenvalue and V is the corresponding eigenvector, then they satisfy the following. A times V equals to lambda times V. How do you compute the eigenvalue? Well, you could move the lambda V to the left and multiply by an identity matrix, and then you take out V as the common factor. So we'll be seeking non-zero solution for this system of equations where A minus lambda I is the coefficient matrix. So we see that this one trivially has a solution, that is when V identically equals to 0. And then we are saying that we want to find non-trivial solution where V is non-zero. Therefore, you must have that the coefficient matrix is singular. Otherwise, V equal to 0 will be the only unique solution. So if this is singular, that means the determinant of it equals to 0. Okay. So we probably have done this computation for 2 by 2 or 3 by 3 matrices, and we see that computing the determinant of this expression in the end leads to a polynomial of degree n, and this polynomial is called the characteristic polynomial of matrix A. So the lambdas will be the roots for this polynomial. So in general, we will have n eigenvalues counting multiplicity. So one property of eigenvalues of A relating to its power function expression is the following, involving the A inverse. Okay. So if you have already found an eigenvalue for A, then 1 over this eigenvalue for A becomes an eigenvalue for A inverse. Now this has the following implication. The L2 norm of A inverse, which we know from before, becomes the maximum over all the eigenvalues of A inverse. And using what we have just discovered here, the eigenvalue of A inverse equals to 1 over the eigenvalue of A. And if we want to take the maximum of this guy, and then the maximum is reached when the denominator reaches its minimum. So it's 1 over the minimum of all the eigenvalues of A. So this relation here later on will be useful when we talk about condition numbers of a matrix A.